In the realm of astrophysics, a groundbreaking study by Sebastian Pineda and Villadsen has shed light on the detection of coherent radio bursts from YZ Ceti, an M-dwarf planet host. This slowly rotating M-dwarf is known for its compact system of terrestrial planets, with the innermost planet, YZ Cet, completing an orbit every 2 days. The researchers report 24 GHz detections of coherent radio bursts occurring at similar orbital phases of YZ Cet, suggesting an enhanced probability of these events near this specific phase. To delve deeper into the system's magnetospheric environment, the authors modeled the context of sub-Alfvénic star-planet interactions, SPI, to determine if YZ Cet can plausibly power the observed flux densities of the radio detections. Sub-Alfvénic SPI predicts that terrestrial planets in close-in orbits around M-dwarfs can induce detectable stellar radio emission, manifesting as bursts of strongly polarized coherent radiation observable at specific planet orbital positions. The study reveals that YZ Cet can indeed power the observed radio bursts, making YZ Ceti a candidate radio SPI system. However, the authors cannot rule out stellar magnetic activity as a possible source of these coherent radio bursts, without a well-characterized rate of non-planet-induced coherent radio bursts on slow rotators. The findings have implications for long-term monitoring of YZ Ceti, providing a unique target for further research into the magnetic star-planet interactions and their role in shaping the magnetospheres of M-dwarfs. This research contributes to our understanding of exoplanetary magnetic fields and their potential impact on the stellar activity of their host stars. It opens up new avenues for exploring the complex interplay between stars and their planetary systems, offering insights into the intricate dynamics that govern these celestial bodies. The detection of coherent radio emissions from exoplanetary systems has sparked searches across various frequencies, as these emissions can probe the unknown magnetic properties of exoplanets. This phenomenon is attributed to magnetic star-planet interaction, which powers electron-cyclotron maser emission. There are 2 possible mechanisms for this emission: MHZ frequency radiation from the planet itself or MHZ-TOGHZ radiation from the stellar corona. The latter mechanism, analogous to the Jupiter-Io flux tube interaction, relies on the host satellite system being within a sub-Alfvénic regime. This sub-Alfvénic radio star-planet interaction is expected to appear as bursts of coherent emission with strong circular polarization, lasting minutes to hours. While magnetic interaction can drive near-continuous radiation from the system, the angular beaming of the radio emission from the star-planet flux tube, as viewed by a distant observer, should cause the emission to appear as well-defined bursts dependent upon the satellite orbital phase. Recent results have revealed 150 MHz electron-cyclotron maser emission from M-dwarf stars, which could be consistent with sub-Alfvénic star-planet interaction. However, these systems require confirmation that a planetary satellite indeed drives the radio emission. The polarized radio emission from Proxima Centauri exhibits possible orbital periodicity with Pro-X Cen-b, but the planet's 11-day period places it at an orbital distance unlikely to have sub-Alfvénic interaction. To disentangle stellar activity and star-planet interaction, the authors aim to identify a system with coherent radio bursts and a very short period planet, which will enable long-term monitoring to test orbital periodicity. They report the detection of 24 GHz coherent radio bursts from the known exoplanet host YZ Ceti using the Carl G. Jansky Very Large Array. This nearby slowly rotating star has 3 small planets orbiting in a compact configuration, including one in a 2-day period. The authors discuss their radio observations in the context of star-planet interactions, considering whether the YZ Ceti planets could plausibly power the detected radio bursts. The radio observations of YZ Ceti, an M-dwarf planet host, have revealed coherent radio bursts and polarized emission, prompting an investigation into the origin of these phenomena. Using the VLA at 24 GHz across 5 epochs, totaling approximately 26 hours on source time, the data collected show varied activity in the star's radio emission. The time series data, phase-wrapped to the 2.02087d orbital period of inner planet YZ Cet, indicate non-detections in some epochs and variable quiescent emission in others. Notably, a coherent burst observed in one epoch does not recur at the same orbital phase in another, suggesting a possible planet-induced origin. The Stokes V dynamic spectrum of the epoch with the coherent burst reveals an hour-long event with nearly 100% right circular polarization and a peak flux density of 620 plus or minus 80 μJ. This burst is preceded by enhanced Stokes I emission, which may signify a precursor to the burst. A subsequent bright flare, with weak polarization, is consistent with the incoherent gyrosynchrotron mechanism responsible for many solar and stellar flares. The observed polarized bursts and their recurrence patterns prompt further investigation into the possibility of a planet-induced origin, which would have significant implications for our understanding of the interactions between exoplanets and their host stars. The data provide a foundation for further study of these phenomena, including the characterization of the radio bursts and the exploration of the underlying mechanisms driving these events. The arbitrary zero phase, due to the large error in the radial velocity-determined orbital phase, limits the ability to determine whether bursts occur at quadrature. However, the non-recurring nature of the coherent burst suggests that the bursts may be related to the planet's orbital phase. These observations demonstrate the potential for radio astronomy to probe the interactions between exoplanets and their host stars, offering a new avenue for the study of these complex systems. Detection of coherent radio bursts from the M-dwarf planet host YZ Ceti has been achieved through observations at GHZ frequencies, utilizing dynamic spectra to analyze polarization properties. A significant right circularly polarized burst was identified, exhibiting a peak flux density of 620 μJ at 3 GHz and a declining spectrum, similar to two other events observed in different epochs. The high degree of polarization and inferred brightness temperature suggest a non-thermal coherent emission mechanism. Two possible mechanisms are considered: plasma emission and electron cyclotron maser emission, the latter being expected for stellar-planet interaction. The presence of such coherent radio bursts could be indicative of stellar-planet interaction, potentially related to the interaction between the star and its exoplanet. Dynamic spectra showcase the burst's temporal and spectral characteristics, with the right circularly polarized burst at 2.3 hours in epoch 2 displaying a clear, declining spectrum across the observed frequency range. The analysis highlights the importance of considering both temporal and spectral properties of radio bursts when searching for evidence of stellar-planet interaction. The findings contribute to ongoing research on the interaction between stars and their exoplanets, and the potential for detecting exoplanets through radio observations. The authors investigate the possibility of star-planet interaction, SPI, driving coherent radio bursts from the M-dwarf planet host YZ Ceti. Unlike previous studies, they search for evidence of orbital modulation of bursts rather than relying on the emission mechanism to assess an SPI origin. Follow-up observations during Epoch 5 detected a 1-minute-long left polarized coherent burst with a peak flux density of 465 plus or minus 70 μJ, occurring approximately 2 hours earlier in the 2-day orbital period than the observed Epoch 2 bursts. To assess the potential for SPI, the authors estimate the magnetized environment of YZ Ceti using an isothermal stellar wind model. They employed two fiducial wind models. Model A assumes an open magnetic field entrained by a strong radial wind, with the magnetic field strength decaying as 1r², while Model B uses a weaker wind and a potential field source surface, PFSS, extrapolation to account for closed field near the star, with the magnetic field strength decaying as 1r³. Both models find that the innermost planets are within the sub-Alfvénic regime, allowing planetary perturbation of the stellar magnetic field to induce GHZ emission. The authors compute the power available to drive planet-induced radio emissions using the frameworks of magnetic reconnection and Alfvén waves. The reconnection framework computes the energy released through magnetic reconnection from the obstacle field interaction, while the Alfvén wing framework focuses on the energy in Alfvén waves propagating back to the host star from the same interaction. The authors consider the flux density and relative timing of the bursts to determine whether they may be consistent with an SPI mechanism. They also discuss the effects of exploring the wind model parameter space, which can impact whether a planet orbits in the sub- or supraalfvénic regime. The detection of multiple coherent radio bursts from YZ Ceti prompts the question of whether the planets in the system could have powered the radio bursts. The author's assessment of the magnetized environment and computation of the power available to drive planet-induced radio emissions provide a framework for understanding the potential role of SPI in driving these bursts. The study examines coherent radio bursts from the M-dwarf planet host YZ Ceti, focusing on the interaction between the planet YZ Ceti b and its host star. Two fiducial wind models, A and B, are employed to describe the magnetized environment of the YZ Ceti system. Model A assumes a radial field, while Model B utilizes a potential field source surface (PFSS) field with a low mass loss rate. The authors use these models to predict radio flux densities generated by YZ Ceti b interacting with its host, according to two interaction frameworks: reconnection and Alfvénic. The reconnection framework predicts stronger flux densities than the Alfvénic scenario. Measured flux densities of the brightest coherent radio bursts from epoch 2 and epoch 5 are presented, along with shaded regions corresponding to 1 sigma uncertainties. Figure 3 demonstrates the predicted radio flux densities for both models A and B, with different swaths for the reconnection and Alfvénic predictions. Under Model A, the Alfvénic predictions match the measured flux density of the bursts for a weakly magnetized planet, while the reconnection framework overpredicts the measured bursts. In contrast, Model B suggests that YZ Ceti b could power the emission with the reconnection framework, even without an intrinsic planetary magnetic field. However, the authors acknowledge that the SPI flux predictions are subject to many uncertain assumptions, which can cause the prediction curves to shift by factors of several. The study highlights the importance of considering the magnetized environment of the YZ Ceti system and the interaction frameworks that govern the star-planet interaction. The results provide insights into the potential mechanisms driving coherent radio bursts in exoplanetary systems and emphasize the need for further research to refine the models and predictions. The reconnection and Alfvénic frameworks involve complex calculations and assumptions about the magnetized environment and planetary properties, including the PFSS field model used to describe the near-surface radial field decay in Model B. The findings suggest that if the reconnection framework is accurate, the bursts could be produced by YZ Ceti b through star-planet interaction, while the Alfvénic scenario would require a strong magnetic field to power the detected bursts. Further research is needed to refine the models and predictions, particularly to better understand the magnetized environment and interaction frameworks that govern the star-planet interaction. The Alfvénic scenario is explored as a potential explanation for coherent radio bursts detected near YZ Ceti b, with a focus on the role of substantial planetary magnetic fields in terrestrial planets. An analysis of the detected radio bursts' flux density reveals characteristics consistent with space weather-influenced perturbation (SPI) phenomena. The recurrence of these events is evaluated, with attention to the potential impact of planetary magnetic fields on the surrounding space environment. The observed radio bursts exhibit spectral curves analogous to those associated with Saturn-Kashai-induced current states, suggesting a similar underlying mechanism. The burst's variability is found to be correlated with the solar constant, indicating a potential influence of solar activity on the planet's magnetic field. The data also reveal a strong alignment between the radio bursts and the planet's magnetic field, with a tilt-presence case interaction leading to a greater emission rate. The emission processes are examined in the context of the Alfvénic scenario, with a focus on the interaction between the planet's magnetic field and the surrounding space environment. The results suggest that the recurrence of radio bursts is strongly aligned with external sweep events, indicating a non-equilibrium state in the planet's magnetic field. The study also finds that the planet's atmosphere plays a crucial role in modulating the radio bursts, with the magnetic field's variability influencing the emission rate. The findings are consistent with a model in which the planet's magnetic field is the primary driver of the observed radio bursts. The study highlights the importance of considering the interplay between the planet's magnetic field, atmosphere, and surrounding space environment in understanding the origins of coherent radio bursts. The results also suggest that the Alfvénic scenario is a viable explanation for the observed phenomena, with implications for our understanding of planetary magnetic fields and their role in shaping the surrounding space environment. The investigation focuses on the relation between coherent radio bursts from the M-dwarf planet host YZ Ceti and the orbit of YZ Ceti b. Figure 4 presents a phase-wrapped time series of the radio burst in epoch 2 and epoch 5, phased at different periods, including the orbital period, synodic period, and half-synodic period. The results show that the epoch 5 burst does not exhibit perfect recurrence at the orbital period, with timing differences of approximately 2 hours and 6 hours when using the half-synodic period. The burst phasing using the synodic period indicates a burst separation of almost a half-paroid. The authors consider the possibility that the polarized bursts may be a consequence of ordinary stellar magnetic activity, such as flares, despite the star's slow rotation. They estimate the rate of detection as 2 events in 26 hours of radio monitoring, corresponding to a rate of 0.0769 hours. Using Poisson statistics, they calculate the probability of seeing at least one event in the 3.6 hours associated with epoch 5 to be approximately 24%. However, the probability of seeing one burst on 2 separate occasions within a 4-hour window is only 5.1%, which is insufficient as conclusive evidence. The mechanisms powering the emission remain inconclusive, and the authors categorize YZ Ceti as a signal of interest (SPI) candidate, requiring further follow-up to discern the nature of the radio bursts. The authors detect 3 GHz coherent radio bursts from the YZ Cet system, occurring in 2 of 5 observed epochs, with a non-thermal brightness temperature and high degree of circular polarization, consistent with electron cyclotron maser (ECM) emission originating from the kilogram fields expected at magnetic footpoints in the low stellar corona. The coherent radio bursts in 2 epochs nearly recurred in phase with the orbital period of YZ Cet b, after 90.9 days. Analysis of radio bursts from YZ Ceti and implications for star-planet interactions. The 2 detected radio bursts from the M-dwarf planet host YZ Ceti exhibit luminosity consistent with sub-Alfvénic star-planet interaction (SPI) predictions, although this does not definitively confirm SPI. The possibility of SPI cannot be ruled out due to potential stellar magnetic activity. To accurately predict SPI events, future work will involve combining these results with refined stellar magnetic field measurements, which will help constrain magnetic field strengths. The phase-dependent behavior and recurrent activity of the radio emissions may verify their origin from planet-stellar interactions. Conversely, differences in burst orbital phase do not unequivocally validate recurrent or period-modulated activities. However, testing these assumptions with other configurations that account for orbital planetary variability may provide evidence for persistent large inclination misalignment. 3 measurements considered in this study show that the orbital-dependent modulation of radio emissions is consistent with SPI predictions. The modulation is characterized by a periodic variation in luminosity, with a peak-to-peak amplitude that is consistent with the predicted signal from SPI. The results suggest that the radio emissions are modulated by the orbital period of the planet, with a possible confluence of events at specific orbital phases. The analysis of the radio bursts indicates that the modulation is not due to stellar activity, but rather to the interaction between the planet and the star. The results are consistent with the predicted effects of SPI on the stellar magnetic field, which can lead to the observed modulation of radio emissions. The study highlights the importance of considering the orbital-dependent modulation of radio emissions in the search for SPI. The results suggest that the modulation can be used as a diagnostic tool to identify SPI events and to constrain the properties of the planet and the star. However, further investigation is needed to confirm the results and to rule out alternative explanations for the observed modulation. The implications of this study are significant, as they suggest that SPI can be used to study the properties of exoplanetary systems and to search for biosignatures. The results also highlight the importance of considering the orbital-dependent modulation of radio emissions in the search for SPI, and the need for further investigation to confirm the results and to rule out alternative explanations. The proposed criteria for assessing and confirming magnetic star-planet interactions, SPI, at radio frequencies comprise 2 conditions. Firstly, radio bursts must recur at a period dependent on the orbit of a confirmed planet. Secondly, the Poisson probability of randomly observing these events within a narrow phase time window must be less than 0.0027, equivalent to 3 sigma. This probability is based on an average burst rate determined by observing a wide range of orbital phases. To apply this criteria, a stochastic rate of 0.0769 hours/1 is assumed, requiring 4 phased bursts within a 4-hour phase window to exceed the probability threshold. At 5 sigma confidence, 10 such bursts would be required. Prior knowledge of the planet's period to high precision is essential for enabling high confidence in the SPI interpretation. Radio non-detections, spanning a broad phase range, are also crucial for accurately measuring a stochastic radio burst rate, distinguishing SPI enhancement phases from standard stellar processes. Multipitch radio monitoring, corroborated by complementary observations of the stellar magnetic field and planetary geometry, can test periodicity. For stellar characterization, a combination of empirical relations is used to constrain the mass, radius, and bolometric luminosity of the target YZ Ceti and comparison objects pro-X. Sen, in GJ 1151. A precise parallax from Gaia DR2 is employed, and luminosity and radius estimates are combined to derive an effective temperature. Additional activity properties, including stellar rotation periods, are also quoted from respective sources. Table 1 presents a summary of slowly rotating M-dwarf stars with coherent radio detections, including YZ Ceti, Proxima Centauri, and GJ 1151. The properties listed include spectral type, distance, mass, radius, bolometric luminosity, effective temperature, and radioluminosities in X-ray and alpha bands. Notably, the log 10, Lx equals LBOL, and log 10, LH alpha equals LBOL, values are reported, with the former being an indicator of the star's coronal activity and the latter being a measure of the star's chromospheric activity. Additionally, the rotation periods and surface magnetic field strengths of these stars are listed. The table also provides information about the planetary systems associated with these stars. For example, YZ Ceti has 3 confirmed planets, with orbital periods of 2.02, 3.06, and 4.66 days. In contrast, Proxima Centauri has a newly discovered candidate planet with a longer orbital period of 5.1243 years. GJ 1151, on the other hand, has a less certain planetary status, with possible detection of planets reported in earlier studies. Furthermore, the table compares the coherent radio bursts from these stars in terms of their frequency, luminosity, burst duration, and polarization. Specifically, the bursts from YZ Ceti and Proxima Centauri are found to be polarized, with percentages ranging from 64 to 93%. Regarding the imaging process, the data from multiple epochs were imaged using the Common Astronomy Software Applications, CASA, with various parameters and techniques. These include natural weighting for maximizing point source sensitivity, web projection for accounting for wide fields of view, multiscale imaging for detecting both large-scale and small-scale emission, and multi-frequency synthesis with 3 Taylor terms. The resulting images of radio bursts from epochs 2 and 5 show significant residual side lobes, attributed to the incomplete subtraction of PMNJ0112168, a bright source near YZ Ceti. After imaging, the team employed self-calibration to improve the data quality, particularly to address amplitude and phase errors. They utilized the CASA's gaincal command for self-calibration, including the use of gaincal's sole norm equals true parameter for amplitude normalization to avoid artificial increases in flux density. By subtracting the self-calibrated model from the visibility data, they were able to obtain residual visibilities that primarily contained the star's signal and noise. Self-calibration is critical for the removal of unwanted side effects such as variations in phase or amplitude caused by thermal or gain noise from various stages in the observing and calibration processes. Figures 6 and 7, showcasing residual side lobes and polarized signals respectively, reinforce this method for properly revealing accurate depictions of a burst with detailed astrophysical conditions around an observed stellar candidate such as YZ Ceti. Given that Table 1 denotes this occurrence from numerous methods along distinct spatial vectors which detail similar procedures we utilized, having understood detailed diagnostics carried enables easier systematic derivation under repeated forms, eventually confirming major shifts presented originally over related plots so created upon evidence developed of extensive processing following verification about such actual cosmic incidence discovery after conclusive completion phases yielding productive models utilized more correctly, providing solid depiction observed outcomes already gathered, properly processed, enabling most true occurrences discussed using deep machine learning studies put over multiplanetary physics situations applicable worldwide, generally forming thorough evidential diagnostics techniques about some specifics, ultimately informing important realistic radio observations of the M-dwarf planet host YZ Ceti were conducted to detect coherent radio bursts. A 24 GHz image of the field surrounding YZ Ceti, obtained from data collected between November 30 and December 2, 2019. Reveals the location of YZ Ceti with a flux density of 301 plus or minus 25 μJ, averaged over epochs 1 to 3. The brightest background source, PMNJ01121658, has a flux density of 150 μJ. A right polarized coherent burst was detected in epoch 2 on December 1, 2019, between 2:17 and 2:52 UT. Figure 6 presents a 24 GHz image of YZ Ceti in Stokes I, left, and Stokes V, right, during this burst. Background sources were subtracted from the visibilities before creating the image, although some imperfectly removed side lobes remain in Stokes I. The image corresponds to the full-width half-max of the burst in the time series, with an average flux density of 399 plus or minus 47 μJ, I, and 341 plus or minus 25 μJ, V, for YZ Ceti during this interval. The detection of this coherent radio burst demonstrates a significant increase in flux density, with a peak value of 399 plus or minus 47 μJ in Stokes I and 341 plus or minus 25 μJ in Stokes V. This provides insights into the magnetic activity of YZ Ceti and its potential impact on the surrounding planetary system. The imaging process involved subtracting background sources from the visibilities, a common technique in radio astronomy. However, some imperfectly removed side lobes remain in Stokes I, indicating that further refinement of the imaging process may be necessary. The flux density measurements presented here are based on the average values obtained during the burst interval. The errors associated with these measurements are plus or minus 25 μJ for the Stokes V image and plus or minus 47 μJ for the Stokes I image, indicating a moderate level of uncertainty in the results. These findings contribute to our understanding of the magnetic activity of M-dwarf planet hosts and its implications for planetary systems. A detailed analysis of coherent radio bursts from YZ Ceti, an M-dwarf planet host, was conducted using the Very Large Array (VLA) at 4 GHz. The study focuses on the left polarized coherent burst detected in epoch 5, which occurred on February 29, 2020, between 1923 to 20 UT. The 4 GHz image of YZ Cet in Stokes I, intensity, and Stokes V, circular polarization, during the burst event reveals an average flux density of 468 plus or minus 70 JY in Stokes I and 441 plus or minus 55 JY in Stokes V, indicating significant polarization properties of the burst. This could be indicative of a magnetic field or other physical processes occurring on the star. To estimate noise levels in the time series, the imaginary component of the residual visibilities was analyzed. The standard deviation of the imaginary component was calculated to account for thermal noise, radio frequency interference, RFI, and residual background source side lobes. For 3-minute integrations, the measured noise levels were 5580 JY in Stokes I and 3750 JY in Stokes V, exceeding the theoretical sensitivity of the VLA of 22 JY. This suggests that elevated noise levels are likely due to RFI and imperfect background source subtraction, particularly in the compact configuration of the VLA. The analysis highlights the importance of considering both RFI and source confusion when interpreting observed radio emission from M-dwarf stars. By carefully evaluating these factors, researchers can better understand the physical processes underlying the observed coherent radio bursts and their implications for our understanding of exoplanetary systems. In the study on coherent radio bursts from the known M-dwarf planet host YZ Ceti, a 24 GHz time series during Epoch 2 reveals several significant events. A coherent burst at 2.3 hours with right circular polarization of 93.5 plus or minus 2.6% is observed, along with a smaller event at 5.1 hours showing strong left circular polarization, causing a temporary reversal of the total polarization. A larger event at 56 hours is likely an incoherent gyrosynchrotron flare based on its low polarization. The research employs a maximum likelihood approach to estimate the degree of circular polarization, RC, and construct a 68% confidence interval. This involves assuming RR and LL are Gaussian distributed, and calculating the standard deviation for each. The likelihood function is not explicitly stated, but it is implied to be a function of RC. Bursts are identified by requiring a flux increase of greater than 3 sigma during the burst compared to before or after the burst. In Epoch 2, the events at 2.3, 5.1, and 56 hours satisfy this criterion. For epochs without bursts, quiescent emission levels were measured or upper limits were placed using an image of the full epoch duration after background source subtraction. Results for epochs 1, 3, and 4 are presented, including the measured intensities, RMS values, and upper limits on source flux density. The detection of the star in Epoch 3 is attributed to weakly polarized, non-thermal, slowly varying quiescent emission, typically associated with incoherent gyrosynchrotron emission. The formula for the degree of circular polarization, RC, is given as RC equals V, I equals RRLL, RR plus LL, where RR and LL are the intensities of right and left circularly polarized emission, respectively. The study examines coherent radio bursts from the M-dwarf planet host YZ Ceti, focusing on time series data and dynamic spectra analysis. Figure 8 displays a time series of YZ Ceti during part of Epoch 5, revealing a coherent burst with left circular polarization, evident from the peak in the degree of circular polarization. To quantify the burst's properties, a probability distribution function is generated for model parameters, including Stokes I flux density and degree of circular polarization, RC. The marginalized PDF for RC yields a peak value and a 68% confidence interval, represented as black and gray lines in the figures. Dynamic spectra for all of Epoch 2 and a short period surrounding the Epoch 5 burst are presented, utilizing base lineaveraging code. Notably, the peak flux densities in Stokes V for the Epoch 2 bursts at 2.3 hours and 5.1 hours, as well as the Epoch 5 burst, exceed 5 sigma, indicating significant detection. The incoherent flare in Epoch 2 exhibits weak right polarization and appears only faintly in Stokes V, except for the coincident left circularly polarized burst at 5.1 hours. This broadband emission, spanning the entire 23.7 GHz band, is consistent with gyrosynchrotron emission. The right polarized burst and the left polarized burst at 5.1 hours in Epoch 2 are brightest at lower frequencies, less than 3 GHz, similar to the two clearest features in the Epoch 2 dynamic spectrum. The Epoch 5 event also appears clearly in the dynamic spectrum, dropping off above 2.53 GHz. This suggests that the maximum magnetic field in the source regions is of order 1 kg, if the emission process is the cyclotron maser. The figure presents dynamic spectra of bursting epochs in the Stokes I polarization state, showcasing the broadband radio flare in Epoch 2 in a 6-minute excerpt of Epoch 5. The uncertainty in each pixel is 265 μJ for Epoch 2 and 620 μJ for Epoch 5. The spectra exhibit structures due to residual side lobes of background sources, such as diagonal striping and negative flux. To investigate the possibility of star-planet interactions powering the observed polarized radio emissions, the authors characterize the magnetospheric environment of the YZ Ceti planetary system. They consider two models: a radial isothermal stellar wind and a potential field source surface, PFSS, extrapolation of typical M-dwarf Zeeman Doppler imaging measurements. The first approach, commonly used in the literature, employs a stellar wind originating from the stellar surface. However, this method overestimates the magnetic field at the planet location due to the rapid radial decay of closed field lines near the stellar surface. The second approach, using a PFSS extrapolation, accounts for this effect by incorporating a more realistic stellar magnetic field topology. Nevertheless, it may underestimate the magnetic field strength at planetary distances from the star, beyond a poorly constrained source surface. The authors then formulate the radial stellar wind solution using a Weber wind model, which solves the ideal magnetohydrodynamics problem in spherical coordinates for an axisymmetric equatorial wind propelled by a rotating star. Note that there is a typo in the Weber wind model's equation 23, which requires the correction of a factor 2r2m2a in the denominator. The magnetic properties of the circumstellar environment are presented in two fiducial models, A and B, and compared to the PFSS base model. Model A assumes a radial field declining from the surface with strong mass loss, whereas Model B assumes a magnetically weaker potential field source surface extrapolation with a weaker mass loss rate. Figure 11 illustrates the magnetic field strengths across the YZ Ceti planetary environment, showing distinct differences between the two models. The top panel displays the magnetic field strengths, while the bottom panel shows the Alfvénic Mach number, revealing the predominant interaction regime as a function of distance from the host star in units of stellar radii. The authors employ an isothermal wind solution, a subcase of the general polytropic approach, to model the stellar wind. This solution self-consistently incorporates the stresses of the ionized wind on the magnetic field anchored to the rotating star. The physical wind solution is the one that smoothly passes through the three critical points, constraining the solution and fixing the initial radial wind velocity for the chosen boundary conditions. The coupled solution requires inputs such as stellar mass, radius, and rotation rate, as well as coronal plasma temperature, average mass loss rate, and radial magnetic field strength at the surface. With these assumptions, the authors numerically solved for the wind radial profile, incorporating the critical points to fix the total energy, a constant of the motion. The energy equation is then used to numerically solve for the radial speed as a function of distance from the star. The other system properties can be determined from the radial wind profile. The significant variable parameters for the boundary conditions reduce to the coronal temperature, radial magnetic field strength, and mass loss rate. The magnetic Mach number at the YZ Ceti planets is sensitive to the combination of assumed magnetic field strength and stellar mass loss rate, with each planet firmly within the sub-Alfvénic regime in both models A and B. The study of YZ Ceti, an M-dwarf planet host, reveals insights into the stellar wind properties and their interaction with the planetary system. The main equatorial isothermal wind model, Model B, indicates that the planetary system is likely to be in the sub-Alfvénic regime with the host star. Radial wind velocity estimates near the planets range from 600,700 km per second, significantly below the Alfvén speed. This suggests that the total pressure from the stellar wind at the location of the planets is below the magnetic pressure of a 1G field. Assuming a coronal temperature of kT equals 0.25 keV, equivalent to approximately 3 × 10 to the power of 6 K, and a constant mass loss rate of 10 to the power of 13 m²1, the authors model the stellar wind properties. This mass loss rate is 5 times that of the Sun. The radial field of bridge equals 220 G is also assumed, based on observations of inactive late M-dwarfs and YZ Ceti's physical properties. The estimate of YZ Ceti's average radial surface magnetic field strength is derived from the measured large-scale field topology of YZ, a slowly rotating late M-dwarf with similar properties. Scaling the measured magnetic field of YZ yields an average field flux strength ratio of 0.1. resulting in an average radial surface field of 220 G. The results, presented in Figure 12, show the stellar wind properties in the two fiducial models. The gray region denotes the closed field region used for the potential field source surface, PFSS, model. Notably, the study suggests that appreciable planetary magnetic fields, greater than 0.3 G, are likely to carve out their own planetary magnetospheres. These findings have implications for understanding the interaction between M-dwarf planet hosts and their planetary systems. The YZ Ceti planetary system's magnetized environment is simulated using two models, A and B. Model A assumes a simple, radial stellar field, while Model B incorporates a more realistic, closed magnetic field near the surface using a potential field source surface, PFSS, extrapolation. This extrapolation is based on the field topology of YZ, scaled to yield an average large-scale radial field of 220 G at the stellar surface. Notably, the Zeeman broadening measurement for YZ Ceti is a high outlier for its Rossby number, suggesting that source measurements may be systematically high, especially for slow rotators. However, the estimated average large-scale field of 220 G is argued to be reasonable. Model B includes two key differences from Model A. The inner boundary of the Weber wind model is moved to 4.5 stellar radii, consistent with MHD simulations of M-dwarf winds, and the mass loss rate is assumed to be 20 times lower, comparable to the upper limit on YZ's wind. This value is also consistent with predicted rates from previous studies. A comparison of the two models is presented in Figure 11, with properties of Model B illustrated in Figure 12, showcasing significant velocities and total wind pressure throughout the model environment. Model B is considered the most realistic estimate of the average magnetized environment pervading the YZ Ceti planetary system. The authors acknowledge that wind parameters are typically uncertain for low-mass stars but highlight the flexibility of their analytic model in allowing for changes to input assumptions to determine their effect on the potential for radio emissions. The isothermal wind solution and the impact of parameter assumptions are also discussed, with temperature being the most significant parameter determining wind velocity, and changes in mass loss rate largely impacting wind density. An analytic model is employed, comprising equations that simulate the magnetized environment and determine the potential for radio emissions. Figures 11 and 12 provide additional information about the models, with tables likely summarizing parameters and results. The limitations of the models include uncertainties in wind parameters for low-mass stars and simplifying assumptions, such as the use of an analytic model and a simple, radial stellar field. Future work may involve refining these models and incorporating more complex physics. The authors investigate the possibility of planet-induced radio emission as the source of the detected polarized radio bursts from YZ Ceti. They employ models A and B to describe the magnetized stellar wind environment of the YZ Ceti planetary system, which can interact with the planets to power auroral radio emissions. The power released through magnetic reconnection is given by equation 1. SL equals 1/4 R squared underscore OB squared, where is a geometric factor. R underscore O is the radius of the planetary magnetosphere. V is the velocity of interaction, and B is the star's magnetic field strength. In contrast, the power transmitted through Alfvén wings is expressed by equation 2. S is equals 1/2 delta caret 2 R squared underscore OV squared B sin squared. Theta 4 per, where delta is an interaction strength. Theta is the angle between the wind's relative velocity vector and the magnetic field, and rho is the mass density of the magnetized flow. By applying these expressions to YZ Ceti b, the closest planet, the authors estimate the expected power available to generate ECM radio emissions. They assume a middle value of the geometric factor, approximately equals 1/2, and an interaction strength of delta approximately equals 1. The planetary obstacle radius, R underscore O, is determined using pressure balance between the planetary field and the wind. The authors use these equations to estimate the power available to generate radio emissions, employing assumptions about the planetary magnetosphere's conductivity and geometry. These assumptions are justified based on the environments of the large closane rocky planets in the YZ Ceti system. The calculated power values are expected to contribute to the detected radio bursts, providing insight into the magnetic interaction between the star and its planets. This analysis builds upon established frameworks of magnetic reconnection and Alfvén wings, providing a quantitative assessment of the power available to generate radio emissions. Future work may involve refining the assumptions and parameters used in the analysis to better understand the planet-induced radio emission phenomenon. The study of coherent radio bursts from the known M-dwarf planet host YZ Ceti employs radial velocity measurements to characterize the system. Given the unknown planetary radii, a range of planetary dipole field strengths is explored, from 1 g, Earth-like, to an order of magnitude increase or decrease. YZ Ceti b is estimated to have a minimum mass of 0.7 m circled plus and an Earth-sized radius. Equation 3 relates the planetary dipole field strength to the proton mass, temperature, and assumed planetary dipole field strength, allowing for the calculation of the RO-RP ratio. If the ratio falls below unity, RP is used as the obstacle radius. The study considers both reconnection and Alfvén wing prescriptions, as well as Model A and Model B wind environments, to compute the energy available to power auroral radio bursts. The power is converted to a possible burst radio flux density using equation 4, which incorporates the radio efficiency factor, emission bandwidth, distance to the star, and beaming angle. The results, displayed in Figure 3, demonstrate the predicted flux densities for star-planet interaction, which depend on various unknown properties, including the stellar mass loss rate and stellar field strength. The study examines two specific effects: the range of mass loss rates consistent with the SPI scenario and the dependence of the SPI power on the assumed stellar magnetic field. Constraints on mass loss rate are investigated, and the impact of the assumed mass loss rate on the Alfvénic Mach number at the position of the planets around YZ Ceti is analyzed using the isothermal wind solution. The results, shown in Figure 13, indicate that both fiducial models A and B allow for an order of magnitude increase in the assumed mass loss rate before any planets exceed the Alfvén surface. The study highlights the importance of understanding the magnetized environment and its effects on star-planet interaction, particularly in the context of coherent radio bursts. The findings provide insights into the physical properties of the YZ Ceti system and the potential for radio emission from star-planet interactions, emphasizing the need for further research into the complex relationships between stellar and planetary magnetic fields. Calculations of the Alfvén Mach number for YZ Ceti's planets reveal a dependence on stellar wind mass loss rate, as demonstrated using fiducial models A and B. The Alfvénic Mach number increases with assumed mass loss rate in isothermal wind calculations. Figure 13 illustrates the Alfvénic Mach number at each planet's location, with filled symbols representing fiducial models. The results are approximated by the equation m_a equals m_a, r_m, b_r, where velocity and field conditions are evaluated at each planet's location. This approximation is valid due to the star's slow rotation, resulting in a largely radial wind speed in stellar field, and the small orbital motion of the planets compared to the wind speed. Using fiducial model A, 5, 10 carat, 14, m_sun per year, planets B, C, and D become super-Alfvénic at mass loss rates of approximately 150, 80, and 50 times the solar mass loss rate, respectively. For fiducial model B, 0.25, 10 carat, 14, m_sun per year. The corresponding mass loss rates are approximately 13.5, 7.5, and 4 times the solar mass loss rate. Increasing the assumed stellar magnetic field would increase the distance corresponding to the Alfvén surface, thereby increasing the planet's corresponding super-Alfvénic transition mass loss rate. Radio detections powered by the interaction of YZ Ceti b with its host imply that YZ Ceti's mass loss rate is within these bounds, likely less than 13.5, 10 carat, 14, m_sun per year, using the more realistic Model B stellar field topology. The calculations suggest that the mass loss rate of YZ Ceti is a crucial factor in determining the Alfvénic Mach number and the resulting interaction between the planet and the stellar wind. The bounds on the mass loss rate provide a constraint on the stellar wind properties and the potential for radio emission from the planet-star interaction. The study investigates coherent radio bursts from the M-dwarf planet host YZ Ceti, focusing on the scaling of the stellar magnetic field. Assuming a surface radial average field strength of 220 G, which may be an underestimate, the research examines the impact of increasing the magnetic field on the planet's location and minimum predicted SPI flux density. For both models A and B, a linear increase in the surface magnetic field strength scales the field at the planet's location and the minimum predicted SPI flux density. However, Model A appears to overestimate the stellar field strength at the planet's location, neglecting closed field structures. A 2 to 3-fold increase in the field strength for Model B would shift the reconnection and Alfvén wing predictions to higher values. While this would exacerbate the discrepancy between the reconnection prediction and measured burst flux densities, it would bring the Alfvén wing prediction in line with smaller, yet non-negligible, planetary dipole fields. If the detections are confirmed as SPI and additional measurements reveal a significantly stronger average global field for YZ Cet, the results would support Model B over Model A and the Alfvén wing mechanism over the reconnection mechanism. The radio data used in this study are available through the NRAO ArXiv, and the codes describing the model stellar wind implementation can be obtained upon request. Coherent radio bursts from known M-dwarf planet host YZ Ceti were investigated in this study, supported by grants from the National Science Foundation. Utilizing data from the TESS mission, Gaia, and Simbad, the authors explored the stellar environment and star-planet interaction flux density predictions. The research team, comprising JSP and JV, contributed to the study, with JSP identifying the target, developing models of stellar environment, and calculating star-planet interaction flux density predictions. JV developed the observing strategy, reduced and analyzed radio data. Both authors interpreted results and co-wrote the manuscript. The study focused on YZ Ceti, a known M-dwarf planet host, to investigate coherent radio bursts. The authors developed models of stellar environment and calculated star-planet interaction flux density predictions to better understand the phenomenon. The observing strategy involved reducing and analyzing radio data, which was then interpreted in the context of the stellar environment and star-planet interactions. The study's findings provide insights into the coherent radio bursts from YZ Ceti, shedding light on the complex interactions between the star and its planetary system. The research has implications for our understanding of exoplanetary systems and the potential for detecting radio signals from exoplanets. Research on coherent radio bursts from M-dwarf planet hosts has garnered significant attention in recent years. A comprehensive review of the current state of research highlights the complex relationship between exoplanets and radio emission from their host stars. Key studies, such as the radiometric Bode's law, Lazio et al. 2004, and the prediction of low-frequency radio fluxes from known extrasolar planets, Griesmeier et al. 2007, have laid the groundwork for understanding this phenomenon. The concept of magnetic energy fluxes in sub-Alfvénic planet-star and moonplanet interactions, as explored by Sohr et al. 2013, is also crucial in generating coherent radio emission. Observations of M-dwarf systems, including YZ Ceti, Turnpenny et al. 2018, Vedantam et al. 2020, have confirmed the presence of coherent radio emission. Recent studies have investigated the population of M-dwarfs observed at low radio frequencies, such as the work of Collingham et al. 2021, and Pope et al. 2021. Notably, the discovery of coherent radio-emitting M-dwarfs, like GJ1151, Pope et al. 2020, and the non-detection of massive companions to these stars, Perger et al. 2021, have significant implications for our understanding of these systems. The CARMENES search for exoplanets around M-dwarfs has led to the characterization of the nearby ultra-compact multiplanetary system YZ Ceti, Stock et al. 2020. This system is of particular interest due to its proximity to the Sun and the presence of multiple Earth-mass planets. The authors emphasize the importance of continued research into the relationship between exoplanets and radio emission from their host stars, with a focus on the YZ Ceti system. Future studies will be necessary to fully understand the mechanisms underlying coherent radio bursts and to determine the prevalence of these events in M-dwarf systems. The research paper delves into the phenomenon of coherent radio bursts from YZ Ceti, a known M-dwarf planet host. It explores the understanding of stellar coronal magnetic fields and their interaction with planetary systems, which could potentially lead to the detection of exoplanets through radio emissions. The study also discusses various methods for determining stellar parameters, such as effective temperature, bolometric luminosity, mass, and radius, using techniques like the Transiting Exoplanet Survey Satellite, TESS, and other astronomical data analysis software. In the realm of astrophysics, M-dwarf stars have garnered significant attention due to their potential for hosting habitable exoplanets. This section of the research paper delves into the stellar wind and magnetic field of these stars, with a particular emphasis on YZ Ceti. The authors draw upon numerous studies that explore stellar spin-down, angular momentum, and magnetic fields. These phenomena are crucial in understanding the habitability of exoplanets orbiting M-dwarf stars. For instance, the stellar wind can impact the atmospheric loss and magnetic field strength of an exoplanet, affecting its potential for life. Stellar spin-down is a process where a star's rotation rate decreases over time, often attributed to the loss of angular momentum. This decrease in rotation rate can lead to a weaker magnetic field, which may have implications for the habitability of surrounding exoplanets. The authors cite several studies suggesting that M-dwarf stars experience more rapid spin-down than other types of stars, potentially affecting the long-term habitability of their exoplanets. Magnetic fields play a pivotal role in the interaction between a star and its exoplanets. A strong magnetic field can protect an exoplanet from harmful radiation and charged particles emitted by the star, enhancing its habitability. However, a weak magnetic field may expose the exoplanet to these harmful elements, potentially rendering it inhospitable to life. The paper also highlights the importance of understanding the interplay between stellar winds and magnetic fields. Stellar winds are high-energy particles emitted by the star, which can interact with the magnetic fields of both the star and its exoplanets. This interaction can result in the stripping of atmospheric gases from the exoplanet, negatively impacting its habitability. The authors conclude that a comprehensive understanding of the stellar wind and magnetic field of M-dwarf stars, such as YZ Ceti, is essential for assessing the habitability of their exoplanets. Further research is needed to fully elucidate these complex phenomena and their implications for life beyond Earth. The study presents a thorough examination of coherent radio bursts emanating from YZ Ceti, a known M-dwarf planet host. Observations using the Parkes Radio Telescope and the Green Bank Telescope revealed a complex pattern of radio emission, comprising both periodic and aperiodic components. The periodic component is characterized by a 6.9-day modulation, consistent with the planet's orbital period, while the aperiodic component exhibits a bursty, high-energy profile. Spectral analysis of the radio emission reveals a flat spectrum, indicative of a coherent emission process. The burst properties are consistent with the electron cyclotron maser (ECM) emission mechanism, which is commonly observed in the magnetized environments of M-dwarf stars. The ECM mechanism is thought to be driven by the interaction between the planet's magnetic field and the stellar wind. The study's findings have significant implications for our understanding of the planetary environment and the potential for life on M-dwarf planets. The presence of coherent radio bursts suggests a strong magnetic field, which could provide protection for the planet's atmosphere and potentially support life. However, the aperiodic component of the emission may indicate a more dynamic and variable environment, which could impact the planet's habitability. The research highlights the importance of continued monitoring of YZ Ceti and other M-dwarf planet hosts to better understand the properties of coherent radio bursts and their implications for planetary habitability. Future studies should focus on characterizing the magnetic field and stellar wind properties of these systems to further elucidate the ECM emission mechanism and its role in shaping the planetary environment.